Hi, welcome back to today's live session. I would like to ask you a question today. How many of you, today is the day for plus one, and how many of you are having clarity on the topic of radius of gyration? It is an important concept which is really connected to the rotational dynamics or rotational motion. So, in my experience, for the last 2 decades, almost all of the students are not having clarity on this particular topic, that is radius of gyration. They keep mugging up the concept or equation to solve numericals, to find or to comply with the derivations, everything like that. So I would like to utilize today's live session to give better clarity on the concept radius of gyration. So let us directly dive into the session. Let me share my screen for you. Okay, now clear screen it is. I wanted to give you the clarity on the fundamentals of rotational dynamics. See, whenever a particle or a point mass, let me put it in that way, a point mass like this, it is rotating about an axis like this. Let me put the name P dashed. Let P dashed be the axis of rotation, and this object whose mass is m, which is rotating about this particular axis. So this is the situation given. So whenever it is rotating about this particular axis, we can say that it is revolving around the axis in a certain circular path like this, just like this. Okay. Now, this distance from the axis of rotation acts as the radius of the circular path. Let it be r, small r. So a particle of mass m is rotating about the axis of axis p dashed, and it is at a distance r from the axis of rotation, so that we can understand that it will be taking a circular path with the radius r. So in such a case, the moment of inertia is the rotational equivalent of translational inertia, or simply inertia. We learned the concept of inertia in laws of motion, because it is the inability of an object to change its state, whether it is the state of rest or of uniform motion, by itself. Every object is having some kind of inability to change its state by itself. In a similar way, in rotational motion also, an object in uniform rotation or uniform circular motion is having the inability to change its state of uniform circular motion or uniform rotational motion by itself. Which means, in order to change the speed of rotation from its status of uniform circular motion, some external physical quantity need to act upon that object. Or for an object at rest, if we wanted that object to come into a circular motion, then again some external physical quantity need to act on it. In the case of translational motion, that quantity is called as force, which is defined by first law of motion by Newton. Every object will continue its state of rest or of uniform motion unless it is acted upon by an external unbalanced force. So the first law gives us the clarity on two physical quantities. One is inertia. What is inertia? It is the inability of every object to change its state of rest or of uniform motion by itself. It cannot change its present state by itself, or its natural tendency is to continue its existing state. That is the property called inertia. Inability of an object to change its state by itself. Inertia. Second thing, first law help us to understand a physical quantity called force. What is force? It is that physical quantity which changes or tends to change the state of rest or of uniform motion of an object. That is about the force. So obviously, first law help us to define two important properties. One is inertia and the second one is force. In a similar way, when we are dealing with the concept of rotational motion, the rotational analogy of inertia is called as moment of inertia. And rotational analogy of force is called torque. These are the equivalent quantities or analogies, similar quantities happening in translatory motion and in rotational motion. In translational motion, we deal with inertia. At the same time, in rotational motion, we deal with moment of inertia. In translational motion, we deal with the force, which is the physical quantity or external physical quantity which changes the state of the present state of an object. Whether it is at rest, then it will change the state of rest. Whether it is in uniform motion, either it will increase the speed or increase the velocity, or it will decrease the velocity. That is the role of force in the case of translatory motion. Similarly, in the case of rotational motion, every object has a tendency to continue its state of uniform motion or state of rest, uniform circular motion or uniform rotation, or in its state of rest. It is evident that when we switch off the fan, which is rotating at a constant speed, when we switch off the fan, it takes some time to come to rest. And it is due to the friction or opposing force exerted by the torque. If air was not there, the fan would have rotated with the same speed till the end of the universe. Okay, so the rotating body has a tendency to continue its state of uniform rotation. That we should understand. So, and in this case, in the case of translational motion, mass is the measure of inertia. But in the case of rotational motion, moment of inertia is determined by two parameters. One is mass itself. Second one is radius of circular path, or it is the perpendicular distance between the axis of rotation and the center of mass of the object. Okay. Now, moment of inertia, it is represented by the letter I. It is found to be directly proportional to the mass of the object, which means if you increase the mass, its rotational inertia or moment of inertia will be more, which means if you are taking an object of 50 gram and you are rotating it at a speed of 2 meters per second, rotational speed, okay, 2 meters per second, then it is having a mass of 50 gram. Now, if you are replacing this mass with 100 gram and you are rotating the same at a speed of 2 meter per second with the same radius, both are rotated at the same radius. Okay. Now, whenever you stop applying the centripetal force, both will slow down its speed and will come to rest. So you measure the time taken for the object to come to rest after you stop applying the force. You will find that the time taken will be double in the case of 100 gram mass when compared to 50 gram mass. 50 gram mass will come to rest faster, which means its inertia is less, rotational inertia is less. But in the case of 100 gram, it is more, or it is almost double, which clearly shows that moment of inertia or rotational rigidity, it is another name, is directly proportional to mass. Now, again, I is found to be proportional to square of the radius. If you keep the mass same, say you are dealing with a mass equal to 100 gram, you are not changing the mass. Instead, you are playing with the radius. First, in the first case, you are rotating the mass at a speed 2 meter per second with a radius equal to 2 meter. Okay. Now, you stop applying the force on it. It will come to rest after some time. You measure the time interval. Now, you repeat the experiment by doubling the radius. You increase the radius to 4 meter. You will find that here I is proportional to r square. In the first case, I is proportional to 2 square. In the second case, I1, I2 proportional to 4 square, or I1 by I2 will be equal to 4 by 16, or 1:4. Or simply we can say that I2 will be equal to 4 times I1. This is the relationship. So moment of inertia, by doubling the radius, the moment of inertia becomes 4 times. So the power relation, square relationship is existing between moment of inertia and the radius at which the particle is rotating. So these are the fundamentals related to this concept. Okay. Now, let us discuss another situation. So far, we have discussed about a point object. Now, we are going to discuss about an extended object like this. See, similar axis, let it be PP dashed itself, but this time an object, a rigid body like this, it is rotating about the same axis. Now, in this case, we can break down this object to be made up of very small particles, each of having masses m1, m2, etc. up to mn, a collection of n particles. Or we can take the concept of integration here. Let a particle, a small such particle is having a small mass, an elementary mass dm, and it is at a distance r from the axis of rotation. This be r. Now, whenever this object is rotating about this axis, this element, the small element dm, it also rotates about the axis of rotation, the same axis pp dashed. So what about the small moment of inertia of that particular particle? that is di. It is given by RdM. Now, how can we get, or how can we obtain the total moment of inertia of the entire object? By integrating di, or di is equal to RdM. So integrating RdM, we will be getting the total moment of inertia of the entire object. In this way, we are able to calculate the moment of inertia of any object, any extended object. It is very simple, okay, by having this concept. Now, the concept radius of gyration appears related to this one. Okay, now let us have a look at the misconcept related to radius of gyration. Most of the students, or many of the students, they think that radius of gyration is nothing but the distance between the axis of rotation and the center of mass of the object. Now let this be the extended object, extended body, and let this be the center of mass. And most of the students think that they are having the misconcept that the radius of gyration is the distance between the axis of rotation and the center of mass. But believe me, this is a wrong concept. What is then the radius of gyration? It is defined in such a way that you might get confused the concept of radius of gyration with the center of mass, with the distance between axis of rotation and the center of mass, because it is defined like this. Radius of gyration is the distance between the axis of rotation and a point where the whole mass of the body is assumed to be concentrated, giving the same moment of inertia as that of the object. See, here, if we evaluate the moment of inertia of this entire extended object by the previous method, we will be getting that I is equal to integral R square dm. R square dm. 1 second, let me check the previous step. Yeah, here I have written R dm. It is wrong. It is a mistake from my part. R square dm. Okay, R square dm. I wanted to correct it. Because, see, you consider this one. Here, moment of inertia is defined to be, see, by combining these two expressions, we can write I is equal to mr square in the case of a point object. This is a point object. In that case, we can write it to be mr square. Okay, when m is a constant, I proportional to r square. When r is kept constant, then I is proportional to m. That is the relationship. Now, if we extend that particular relationship to a small object in the case of an extended object, then we are writing the small moment of inertia to be r square dm, or dm into r square. Okay, we are having the freedom to change the order, r square dm or dm into r square. So by integrating this particular expression, we are getting the total moment of inertia of the object. Now, coming to this particular situation, we can evaluate the whole moment of inertia of the body when it is rotating about this particular axis of rotation, which is given by p dashed. Okay, now we have evaluated it, we have calculated it. That part is over. Now, in order to understand the concept of radius of gyration, we are doing something else. Yes, let me change this object. I'm replacing this object and I'm taking a point object. Okay, a point object which is having the same mass as that of this whole body. You think about it. See, this is a point mass, but its mass is equal to the mass of this whole body. So if this body is having a mass m, the mass of this point object is also m. Now, it is at a distance this much, which is given by small r from the axis of rotation. Now, let it rotate about this particular axis. We can calculate the moment of inertia of that particular point object. Okay, let it be I1. I1 equals to, we will be getting m times r square, r1 square. Let it be r1. Now, we are increasing r, keeping the mass same object. Now, I am rotating the same object at a larger distance. Okay, r2. Now, the moment of inertia I2 will be m r2 square. Obviously, I2 will be greater than I1. Why? Mass is same, but we have increased the radius part. Okay, R2 is greater than R1. So we are continuing this process by slightly increasing the value of radius in each experiments or each trials. Now, each time we are measuring the moment of inertia. Okay, then each time we are comparing this value of moment of inertia which we got with the previously calculated value of moment of inertia of this body. We are comparing the value. Okay, now we will understand that this value is approaching closer and closer to the moment of inertia of this extended object. Now, at some distance, when this point object or point mass, whose mass is exactly equal to the mass of the extended object, when it is rotated at a certain specific distance from the axis of rotation, it will be giving the same moment of inertia as that of this body when it is rotated at a distance r from the axis of rotation. Okay. Okay. Sorry, 1 second. Okay. 1 second. I wanted to rework on that. Yes. Okay. So this value will be matching with a particular value you given to R1, R2, R3. You are experimenting with that. Okay. So for some value of R, you will be getting the moment of inertia in that particular case exactly matching with the moment of inertia of the extended object as we found in the previous case. Okay. Now that distance is called as the radius of gyration. So in the case of an extended object, you replace that object with a point object having the same mass as that of the extended object. Now, at what distance from the same axis of rotation, that point mass is giving you the exact moment of inertia, exact value of moment of inertia of the extended object. Then that distance is called as the radius of gyration. Okay. Now, this is having several applications in various situations. By the end of that particular chapter, rotational dynamics, which is a really, really important chapter in +1, you will find the situation of an object rolling down a slope. We are taking 3 situations. One, taking it to be a cylinder. Second case, taking it to be a ring. Third case, taking the object which is rolling down over the slope to be a sphere, solid sphere. In all these cases, we are finding the value of total kinetic energy. We will be equating it with the total potential energy, and using that, we will be finding the maximum velocity when the object is reaching at the bottom of the slope. Okay. And in all those cases, we are dealing with the concept of radius of gyration. So radius of gyration is an extremely important topic, not only for +2, even if you are moving to higher classes at engineering level or some technology or application level, it is extremely important concept. Okay, so I hope this video, this live session gave you better clarity on the concept of radius of gyration. And I thank each one of you for diligently attending this live session till now. Okay. And I would like each one of you having clarity related to the concepts. When you are dealing with a beautiful subject like physics, then only you will be able to enjoy the process, or you will be able to enjoy the subject with deep passion, excitement, enthusiasm, and enjoyment. So enjoy the process of mastering physics. And if you want to know more about learning physics with lots of joy, excitement, and enthusiasm, I wanted to invite you to attend my free webinar called Physics Made Easy. It is a 2-hour long webinar. It is absolutely free. You will be able to get several mind-blown insights from that particular webinar, which will help you to level up the game of physics mastery for you, for your future learning journey and career journey, especially if you are planning to pursue any career related to science. Okay, so I would like to uh, attend my free webinar, which is called as Physics Made Easy. You will be able to find the registration link to register for the free webinar under the description of this particular live video. So I'm signing off for today. Thank you for being with me for this much of time. If you find this time well spent, then please write your valuable comments and takeaways, key takeaways under this video as your comment. Okay, you can you are free to subscribe the channel if you wish to know more about this kind of contents. I will be coming live every day at 6:30 p.m. except Sunday. On Sundays, I'm coming live at 10:30 a.m. IST. On all other days, from Monday to Saturday, I'm coming live at 6:30 p.m. IST on this particular channel. So once again, signing off. Thank you all.